Alright, this is a momentum problem where they're asking about the magnitude and direction of the force exerted on the puck by the boundary. So, alright, so we really can't use, well, let's write down what we know first. So the mass, the initial speed and the final speed are both 12 meters per second. So, but there is a change in momentum. There is a delta p because there's a change in direction, right? This is the initial velocity, and this is the final velocity. All right, and then delta t, the time, is 0.035 seconds. All right, so when we're talking about the impact with this boundary, we can't really use the equations of motion with constant acceleration because the acceleration is not necessarily constant there. Instead, the way we need to approach this is using the definition of impulse, which is, right, if we want, where this is what we're looking for, this average force that's exerted while it impacts the boundary. See, we can get this change in momentum, and we already have the change in time. So let's do that. Let's find what delta p is. So to get delta p, it's a vector. We got to consider both the x and the y directions, right? You know, delta p is equal to p minus p naught. Well, remember with vectors, whether you're adding or subtracting vectors, you have to do it with components, right? If I have a vector a, you know, that is 3 units, and a vector b that is 3 units, and I want to find the vector c, well, c is not 3 plus 3. It doesn't have a magnitude of 6, right? You've got to add up the components. So what we need to do is we need to consider first the x component, which is the final momentum in the x direction minus the initial momentum in the x direction. Final minus initial. Now, as far as sign conventions are concerned, we'll take to the right to be positive, or standard Cartesian, and up will be positive. So let's see, so that's 0.22 is the mass, and then the final velocity is 12 sine 25. Right, here's the final velocity. It has an x component, or it has a y component and an x component. So there's the x component, and here's the y component. So the x component is equal to v sine 25. The x component is the side opposite. And then the initial velocity, the x component points to the left, and the y component points straight up. So that's 0.220 times negative 12 sine 25. So you got to be very careful with your signs here because they're both important. The final velocity, the final x velocity, is positive 12 sine 25, and the initial velocity is negative 12 sine 25. So these two minus signs cancel out. It means you add them together. You add these two terms together to get 2.23 kilogram meters per second. Now if we look in the y direction, then we get, and the final y velocity is 12 cosine 25. It's positive because it points up. And the initial y velocity is also 12 cosine 25 because it points up. And so that adds to 0. So our delta p vector has an x component of 2.23 and a y component of 0. So it's just 2.23 in the positive x direction. Therefore, the average force, which is delta p over delta t, is just 2.23 over 0.035, which is 64 newtons, and it's in the positive x direction, just like the momentum vector.